In this video, we will introduce long short-term memory networks, which are also called LSTMs. So they are the special class of recurrent neural networks that was developed specifically to address some of the difficulties that we saw when training these recurrent neural networks. So let's get started.
Long short-term memory, or LSTM. So before we dive in, I want to quickly point out the connection between the backpropagation through time equations that we saw in the last video and the vanishing and exploding gradients problem that was discussed previously. So if you remember, the calculations of the gradient of the loss with respect to the hidden node activations in the backpropagation through time, then there was this term of the Jacobian of the hidden states at time of t plus 1 with respect to the hidden states at time t. Now, this Jacobian repeats through the recurrent chain and it carries the gradient backwards. So the gradients from time step t before, it carries them backwards towards the gradient at time step that we are currently looking at. And what this means is that this particular term comes from the Jacobian. So the weight matrix W transpose times the diagonal of the derivative of the activations at the time step before. So this matrix is applied repeatedly as we go backwards in time. So first we apply it to the gradient of from the loss with respect to the hidden nodes at time t plus 1. And then at the next time step, we would go back even further. And this whole thing again would be multiplied again by a term that would be same as this one. So just with the derivative here with respect to h at time t. So you can imagine that as we multiply repeatedly with this matrix, we need to look at the eigenvalues of the matrix. And as we discussed before, if we do an eigenvalue decomposition of this kind of a matrix, the eigenvalues for the different components, if they are smaller than 1, then we are likely to get the vanishing gradient problem. And if they are larger than 1, then we likely get the exploding gradient problem. So I'm saying likely here because here we do not have the contributions of the outputs also. So the output contributes to the gradient as well. So that's why it's not easy to exactly say that this does. Nevertheless, if these two cases apply, then it's quite likely that if this happens repeatedly in this chain, then we will get either a vanishing or an exploding gradient problem. So before we now introduce the LSTM and how it addresses these problems of vanishing and exploding gradients, I want to quickly introduce a new visualization of a recurrent neural network unit. So remember before we used these earlier, the computational graph kinds of representations. Now here we are picturing a regular RNN or a vanilla RNN unit where you have inputs X that are coming in at time T, and you have context from the hidden units from the previous time steps coming in, and these are combined with a tanh nonlinear layer here, giving the hidden states at time t, and also contributing to the computations of the output at time t. So if you look at the LSTM, things get a bit more complicated. So these LSTM networks or LSTM cells were introduced quite a bit before in 1997 by Hochreiter and Schmidt-Huber, and they were specifically designed to deal better with the problem of vanishing and also to some extent the exploding gradient problem. So what we have here are basically the memory cells, and these have these special gates. And these gates are basically the key to this entire architecture. So we actually have these three gates. We have a forget gate, an input gate, and an output gate. And these gates can be then trained so that they actually are components with trainable weights by themselves. And they decide what part of the input to let into the cell when to clear the cell, and when to forget parts of the content of the cell that it's already stored, and as well as when to let information into the output stream. So we have different gates here. So if you look at the cell here, just as before,
then we have the forget gate that looks at the new inputs that are coming in and at the from the hidden state from time step h of t minus 1. And then we have the input gate that looks at the new inputs and the hidden state h of t minus 1 to then decide which values would then be updated.
and then we have again the output gate, which then contributes to this part that you see here. So we have a stream that then maps the cell state from one time step to the next with a linear mapping as well. Let's look at this one time step at a time in more detail. So here we see this top line of the cell. So we have the cell state from the time step before, that is C of t minus 1. And this is then combined with the forget gate and also with the input gate that you see here. But in general, this just flows from one time step through the cell and just flows out through the next time step by combining the information of the forget gate and the input gate. Then we have the forget gate at the beginning, as you see here. So the forget gate is referred to as f of t. Now, as I said, this forget gate also has its own set of weights, and it combines with the inputs of the hidden states from the previous time step before and the input x of t at time step t, and it combines them with its own bias, and then everything is put through a logistic sigmoid nonlinearity. So because it's a logistic function here, the output will be between 0 and 1. And we will use that to influence how much of the old cell state we want to keep or how much we want to forget. So in the extreme case, f of t could be set to 0, then you would completely forget the old cell state that you had. And if it's set to 1, then you would completely remember everything that you have in the cell state before. So that's how this controls the information flow. Okay, so we also get new inputs, and we want to let the network decide whether it wants to let it into the cell content. For that, we have trainable input gate I of t, and it's this part here again, trainable input gate I of t, and it has its own set of weights and biases, and it again takes the same input vector at the current time step and the hidden state from the previous time step, and it's again squashed with a logistic sigmoid function which is between 0 and 1. Then we have the candidate cell state or the C tilde sub t, and this again has its own set of weights and its own biases, and it takes the same input as before, the input at current time step as well as the hidden state from the previous time step, and it maps it now through a hyperbolic tangent. So this now can be between -1 to 1. So the candidate cell state is depicted here in the diagram. Then we form the new cell state at time step E by element-wise combination of the forget gate and the old cell contents at t-1, and we decide with the input gate how much of the candidate cell state C tilde that we want to let in. So these both are element-wise operations here. So the nice thing about this is that this is a mapping of C onto itself with an adaptable weight F with this forget gate. And this is realized as an adaptive time constant. So this can be a quick forgetting mechanism, but it can also be set to very high values, and then you would remember the information from the past for a very long time. Plus, you are flexible to how much new information that you want to let in into this cell state here. So that's what happens here. Okay, so the last step is to compute the outputs O of t. Again, we have a set of weights and biases, and we use the same input just as before, as well as the hidden state from t minus 1. And we put this through a logistic function here, which is between 0 and 1. So all of these gates have outputs between 0 and 1. And we use it to decide how much of the non-linearly mapped cell state that do we want to let in into the current hidden state h of t of the LSTM cell. So this is then passed on to the next time step, and as well as to the following cells and so on. So because we have this nice information flow on top here of the cell state C, this means that when we also backprop in the end, here the gradients can flow very nicely. So here we don't really have any multiplications with weight matrix W, so we only have element-wise updation here. So there are also no non-linearities involved. So we have a linear mapping of C onto itself here. So we only have a linear mapping, and we let some new information that we let in through the input gate here, but everything is combined in a linear way. So on top here, the gradients can flow very nicely. So LSTMs are really quite powerful. So they're very flexible with their gating mechanisms, and they can gate the information flow so that the information from the input stream is made internal and comes into the cell state for further computation. So they can also extract features of the current input and add them to the cell state. So they are also able to selectively forget and remember features, and this is really an important property of LSTM cells. So another good point is that we have a clear meaning for these different variables that we use. So we have clear weights that we know belong to different gates. And overall, because of this nice information flow on top of the cell state that we saw, we have fewer problems with weight decay. And this overall leads to much nicer training than the regular RNNs. So there's a nice blog post that I want to mention, and there's also a paper by the same authors. So this is from the blog post of Andrej Karpati. So here in this paper, they looked at an LSTM cell, and after they trained it, they wanted to try and better understand what the LSTM cells actually learn. And then they just basically correlated the activity of the LSTM cells with the different features that they came up with in a brute force way. So interestingly, what they found was some of the cells that when they were trained on, for example, a text prediction task, they found that some of these cells would become sensitive to positions in the line. And that's what you see on the top here. So towards the end of the line, these cells would have higher values, indicating that the end of the line is near. And they also found that some cells, for example, turned on inside these codes. So whenever they encountered a code, then they gave high activation here. So we have cells that also track whenever a quote is open and when a quote is ended. So another property that they saw is that we have cells that robustly activate inside if statements here. So if you have a piece of code that your network is looking at, then we got high activations where specific cells were activated when you have these if statements. But these are only some examples that they found, and many cells that they found here, like in the bottom, are really hard to interpret. So this is what they say here. So if you look at the output of these cells that are shown here, it's really not very clear what they are actually doing. However, it's extracting some kind of features that overall help the network to make correct predictions. All right, so that brings us to the end of this video, and I have 3 questions for you. What are the differences between a vanilla recurrent neural network unit and a long short-term memory cell? The second question is, why are vanishing or exploding gradients less of a problem in LSTM cells? And the final question is, why is it reasonable to say that LSTMs can learn on varying timescales? So that also brings us to the end of this video. I will see you in the next video. Thank you.